Carbohydrates. That word is everywhere, right? In our diets, our workouts, our biology homework. But what are they really? Well, today, we're going to peel back the nutrition label and really decode the sweet science behind one of the most important molecules for life.
All right, so let's get right into it. When I say carb, your mind probably jumps straight to bread, pasta, potatoes, and you're not wrong. But to get what they really are, we have to think less like a chef and a little more like a chemist. We've got to put on our imaginary lab coats for a second. So what's the fundamental identity of a carbohydrate?
At its most basic level, a carbohydrate is just a molecule built from three simple things: carbon, hydrogen, and oxygen. Actually, the name itself gives the whole game away. Carbo for, well, carbon, and hydrate for water, because the hydrogen and oxygen are usually in the same 2-to-1 ratio as H2O. And that other word, saccharide, that's just the sciencey way of saying sugar.
But here's the thing. They do so much more than give you a sugar rush. Yeah, of course, they're a huge source of fuel for pretty much all life on Earth. But they're also builders. They make up the tough stuff like cellulose that helps plants stand up straight. They're a critical piece of our genetic code in DNA and RNA. And they even act like tiny little name tags on the outside of our cells. Honestly, they're like the Swiss Army knife of biology.
So if we want to crack this whole complex carb code, we've got to start small. Super small. We're going to zoom all the way in and start with the absolute fundamentals, the simplest sugars.
And these little guys, these fundamental building blocks, are called monosaccharides. The name is pretty straightforward, right? Mono means one, and saccharide, as we just learned, means sugar. One sugar. You literally can't break them down into anything smaller. They are the individual Lego bricks of the carbohydrate world. So how do we tell these little Lego bricks apart? Well, one of the easiest ways is to just count their carbon atoms. It's a really simple system. A sugar with 3 carbons is called a triose, one with 5, like you'd find in RNA, is a pentose, and the big one, the one you've definitely heard of, glucose, that's a hexose because it has 6 carbons. Okay, but here's where it gets really cool. A tiny shift in how the atoms are arranged creates a whole new kind of sugar. It all comes down to one specific feature: a carbon atom double bonded to an oxygen atom. If that double bond is hanging out at the very end of the carbon chain, we call it an aldose. But if that same bond is somewhere in the middle of the chain, it becomes a ketose. Same exact parts, just put together slightly differently, and boom, a whole new molecule.
And that idea, that arrangement is everything. Well, it leads us to something even wilder. It's not just about a 2D drawing on a page. We're talking about 3D space. Which brings us to a really neat puzzle: the concept of sugar's mirror image.
So, take a look at this. We've got 2 molecules here. On paper, they look like twins. They have the exact same chemical formula, same number of carbons, hydrogens, oxygens, the whole shebang. So, what gives? What on earth makes them different from each other?
The secret has a pretty cool name: chirality. And the hero of this story is something called a chiral carbon. So think of it like this. A carbon atom has 4 hands to hold on to things. When it's holding 4 totally different things, one in each hand, that's when it becomes chiral. That is the magic ingredient that allows it to have a mirror image twin.
And these mirror image twins? They're called enantiomers. Now the key here, and this is super important, is that you can't stack them perfectly on top of each other. It's just like your hands. Go ahead, try it. They're perfect mirror images, but no matter how you turn them, your right palm will never fit perfectly on top of your left palm. Same deal here. They're related, but they are fundamentally different shapes.
So, if we have these left-handed and right-handed sugars, how do we label them? Well, chemists came up with a pretty simple rule. It's called the D and L system. You just find the special chiral carbon that's farthest from the top, and then you look at its little hydroxyl or OH group. If that group is pointing to the right, it's a D sugar. If it's pointing to the left, it's an L sugar. Now you might be thinking, okay, D, L, who cares? Well, your body cares a lot. This is the punchline. Our bodies are almost exclusively designed to use D sugars for energy. You could eat an L sugar and it might even taste sweet, but your cells would be like, nope, can't use this, and it would just pass right through. That's how important shape is. In biology, shape is everything.
All right, let's take a quick breather. We've got our basic Lego bricks, the monosaccharides. We know they can be left-handed or right-handed. So what's next? Well, now it's time to start building something. Let's see how these little guys link up to make bigger and more complex sugars. But wait, there's one more thing we got to cover before we start snapping them together.
You know how we've been looking at them as these straight little lines? Well, that's a bit of a fib. In the real world, especially when they're floating around in water like in our bodies, they don't stay like that. They curl up into rings. So the question is, why?
The answer is something you see everywhere in chemistry and in nature. Finding the comfy spot. It all comes down to stability. The ring shape is just more stable. It's a lower energy state. It's like the molecule is a person who's been standing up all day and finally gets to curl up on the couch. The long chain literally bends around and bites its own tail, forming a bond that makes it more relaxed and stable.
Okay, so now we have our comfy, stable, ring-shaped Legos. Now we can finally start building. So let's do a little pop quiz. What do you think happens when we take 1 unit of glucose and snap it together with another simple sugar called galactose?
Boom, you get lactose. Yep, the exact same sugar that's found in milk. And this is our very first example of a disaccharide. Di means 2, so 2 sugars. Simple as that.
And this simple recipe, just snapping 2 of these monosaccharides together, is how we get all the common sugars you've heard of. Take 2 glucose units and stick them together, you get maltose, or malt sugar. Glucose plus galactose, we just saw that one. It's lactose. And what about good old table sugar? That's just a glucose stuck to a fructose. It's that simple.
But what's the actual glue that holds these units together? It's a special kind of connection called a glycosidic bond. And here's how it forms. For 2 sugars to link up, a tiny molecule of water has to get kicked out of the way. It's called a dehydration reaction. Dehydrate, to remove water. Once that water's gone, the 2 sugars can lock together.
And just like that, we've done it. We started with the tiniest building block, the monosaccharide. We saw how it can have a mirror image twin, and then we watched them link up to build bigger chains. We've officially cracked the basic code of carbohydrates. So, I want to leave you with this final thought. We saw how just flipping one tiny group of atoms from right to left creates a completely different sugar that our body literally can't even use. If a change that small can have such a huge impact, just think about it. What other incredible, mind-bending molecular secrets are hiding in plain sight in the very food you're going to eat for dinner tonight?